So I'm going to run this, and now I want to check and see that that data is correct. So I put the link to the SRA run selector here, but again, you're going to just type this variable into the command line. And you can see here that you could also run it from this line where it will just run this by itself in the console. So you could also just type that. And what it's showing me, and I can view this another way as well. Let's look at that because this is getting a little larger. So you can use this view command to view any object in Rstudio. So I want to look at sample table. You can see it gives me a little tab option here. Using view, and it has to be a capital V, annoyingly. Doing view opens this data in a new tab, basically. So you can see here that we have these shortened sample names. These are actually, this shouldn't even have this GCF in it, but that's fine. We have the file name itself, and then we have the condition and the patient. And so we're not going to do this now, but you might want to go back to this NCBI run selector and just make sure that, SRR blah, blah, blah 38 is the patient number 15 and is the cancerous sample. And then you could check on patient 15's normal sample, and that should be SRR 56. So this is really just a check to make sure that your data is being labeled correctly. It's just sort of the metadata for our analysis. So we're going to be comparing the patient or the cancer condition to the non-cancer condition for these samples. So this line here is the first time that we're going to be using a function from DESeq. And so if DESeq didn't load correctly, this is when you will find that out. So I'm going to go ahead and run that here. I may split this into 2 videos. Yeah, okay. So actually this is perfect. So this tells me that DESeq did not load correctly because when I ran this line, this DESeq line, it says it cannot find this function. That means that the package is probably not loaded. So in that case, I need to go back up to the top and try to reinstall it. So first I'm going to go to this line here. I'm going to just run this library BIOC manager if it makes a difference. I don't think it does. But I'm now going to just try to reinstall DESeq2 and see if there's any issues with that. So I didn't notice there being any issues before, but we don't find out until we're really trying to use the software. It's certainly taking a minute, so that's interesting. Okay, so it said it downloaded everything. Again, I'm going to say I don't want to update these old packages. If it still doesn't work, I may come back and try that. But for now, I'm just going to try to reinstall and then reload the library. So I'm going back down to the library line with DESeq and running that. So it looks like it ran correctly. I don't see anything that says error. I see some things about packages being masked. That, again, relates to this conflict idea. So let's go back down to the line that runs DESeq and try it again. And you can see that this time it worked. So sometimes it really is that simple where we just have to reinstall and reload. Something went wrong the first time that we just didn't catch. So this has run now. It's totally fine if you get this warning message. This is just about a kind of specific data type. That's fine. What's really important here, so again, important line, is this design formula. So in DESeq, this design formula is what tells the DESeq software that's going to decide how genes are, how significantly expressed genes are, how significantly differently expressed genes are, and then their fold change. This design formula tells DESeq how to think about our experiment. So here it's saying test for between conditions, so cancer versus non-cancer, and then control for the effects of patient variation. And so if you run your own DESeq analysis, you will need to probably rework this design formula to fit your specific experiment, and that's something I'll work with all the groups on. So now that this is set up, it's in a count table. We actually can't view the count table because it's getting into a software-specific format. So this DESeq dataset is a very specific format that we can't easily view, right? It says the class is a DESeq dataset. I can see that it has about almost 50,000 genes here because every row is a gene. But we can't really actually see it, and that's fine. We also need to make sure we're setting the normal condition as the reference, right? Because if we're asking the question, how many genes or which genes are differentially expressed, that could be from the normal condition or from the cancer condition. And we want that to be from the normal condition to the cancer condition. So we have to set the normal as the reference. And so that's what this line here is doing. So now is the part where you actually run DESeq itself. So very important to mention DESeq, the software, in your report. I find that a lot of people forget, even though it is the main statistical analysis that we're getting results from. So try to make sure to talk about DESeq and talk about what it does. So this is the line that actually runs DESeq on our count table. So it gives us progress messages about what part of the steps of DESeq methods it's on. So it's looking at the distribution of all of the read coverages for the genes and doing a few statistical transformations and tests. So now I need to turn it into results. Because this, again, is just a DESeq specific kind of data set. I can try to look at it on the console, but again, it's this DESeq data set, so I can't easily see it. So if you view your results, you can just view the partial results because it'll just print the top here. So now that we've turned this into results using this results command, I first want to check and see that the condition is set up correctly. So it should be C versus N, cancer versus non-cancer. If it's reversed, it says here, the p-values won't change, but the fold changes will be backwards, right? Because what is the reference? We're looking at what is it differentially expressed from. And DESeq has more than just cancer versus non-cancer. It tests multiple combinations of things, and you can see that using this results names. So this isn't important here, but it will be important when you're running your own analyses in DESeq for the final project. Because you might want to test things other than just the condition. It might be more complicated, right? If I wanted to look at, compare patient 23 versus 15 or compare the patients, that could be another comparison I could look at. So we'll talk about that more when we get into the final projects. So here I'm just kind of making backups of these file names. Not super important. So the next thing I'm going to do is subset the results data set to make sure that there are only genes that actually mapped. Because in this data set, we also have genes that have no reads mapping to them. That doesn't really help us at all. So it should already kind of remove those, but in some cases the counts are too low to get a p-value from. And so I'm just removing those. That's what this right here is doing. So ones without an adjusted p-value, and remember the adjusted p-value is the one that we're interested in. We're not interested in the regular p-value. We only want to use this p-adjusted, because this has been corrected by multiple testing. Correction. So here I'm just adding the genes as a row, and then, whoops. And then I'm making this into a data frame instead of a DESeq specific data set so that we can actually look at it. So that's what this as data frame is doing. And then I'm making another backup. So let's go ahead and look at this data set. So I just removed this comment here to view this line, and then I'm printing that, or I'm running that line. So this is the data set that is your final output, basically. So all the figures and everything is going to be based on this data frame, where every row is a gene, and the most important columns that we're interested in are the log 2 fold change and the adjusted p-value. So the log 2 fold change again tells us how much change there is. A log 2 fold change of 1, positive 1, would mean that a gene is doubly as expressed in your cancerous condition. If the log 2 fold change is negative 1, that means that the gene is half as expressed. So half as many RNA transcripts, or RNA reads, and also we're assuming transcripts. So this is what tells you about overexpression versus underexpression and the magnitude of that difference, right? How differentially expressed. If it's just a little different, okay. If it's very, very different, that might be more biologically interesting to us. And we can sort on these columns as well by clicking these headers. So we can see that the most downregulated genes in our sample, the most negative, are, I don't know what these genes are. I'd have to look them up. But that's kind of what you'll be doing a little further on. You can also sort by p-value, right? So we could look at the lowest p-value, the smallest p-value. That means the one that is the most significant, the most surprising result. That's our gene here, FLNC. So I can see that it has a low p-value. I can see that it has a negative fold change. That means that it's an underexpressed gene. And anytime you're talking in your report about individual genes, you'll need to reference this data frame and give us the adjusted p-value and the log 2 fold change. Because it's important, right, that we're talking about significant genes and we're also talking about how differently expressed they are. So you'll get that from this data. And you can search genes as well, right? So you can search and find them here. This is a gene that's pretty significant, but it's slightly under, no, actually that's pretty good. But it is underexpressed in cancer, is how we would interpret that. So this is your data frame you'll be pulling data from. We further go on to subset this data by the significant results and by the fold change, right? Because I told you that we need to define what we mean by differentially expressed genes. We need to have a p-value that we're saying this is the cutoff. You'll need to make sure to report that p-value in your reports as well. It's really important that we say which statistical threshold we've set for our data. So here it's 0.05. That means that 5% of our significant DE results will be false positives. That's fine. That's what the adjusted, the multiple testing correction is for. So first I'm just subsetting it by p-value alone. So I'm making a new data frame that's significant results only. The next thing we're doing is just calculating a few things and continuing to subset. So first I might want to compute the percentage of genes that are differentially expressed, here just by p-value. And here only out of the genes with mapped reads, not out of all genes, right? Because remember that a lot of our genes didn't even have reads mapping to them. So we don't need to count that in the denominator. So here if I run this, it tells me that almost 13% of our almost 13% of our genes that mapped are significant with a p-value of 0.05. And that's the way to talk about it, to talk about your p-value. So we want to define differentially expressed genes at minimum by their p-value, at minimum by their significance, but oftentimes we also want to set fold change thresholds as well. So here I'm subsetting it again to see that there are fold changes that are more than twofold. So genes where there's at least a doubling in expression or a halving in expression. So that's what this command here is doing as well. If you want to know more kind of about how these work, I think this is probably a great application for ChatGPT because you could like put this in and then ask ChatGPT to explain each part of it since we don't have time to go into everything here. So now that I've further subset them into both p-value and fold change, I want to recalculate that percentage to see how many genes are what we're calling differentially expressed genes by p-value and fold change. So that's what this line here does. And you can see that definitely reduces the number because we've set another threshold on top of it. So about 6.7, 6.8% of our genes that mapped are differentially expressed and with a significant p-value and with a fold change of at least 2. So you'll need to tell us how you're defining differentially expressed genes.